Autonomous Casting Rover consists of three distinct systems which collect solar energy, heat ISRU-derived feedstock to a molten state, and form mold shapes for the casting of structures directly into the lunar surface. ACRE's subsystems have been validated through experiment and simulation throughout the project. The energy for batch-wise heating of the feedstock carried in the rover is provided by the optical waveguide solar power system, which uses an array of parabolic mirrors to concentrate the powerful and nearly constant solar rays of the lunar South Pole into bundles of optical waveguide cables. The focal points of the mirrors have been validated with a custom stand which points lasers normal to the surface of the mirror. A fog machine makes laser tracing efficient and the experimental focal point can be measured. Once the focal point was found, a mount for the secondary mirror was constructed for the test rig. Outdoor calorimetry testing then ensued. To find the efficiency of each mirror, a black body cylinder was mounted in place of the secondary mirror to absorb all solar energy over a given period of time. The change in temperature over time was recorded and brought back to the lab where a simulation of the black body was generated. The ANSYS transient thermal simulation accounted for the modes of heat transfer acting on the body to match the temperature increase from experiment. The efficiency was then determined by comparing the given solar flux in the area at that time of day to the actual solar power measured by the calorimetry experiment.
The solar concentrator system carries rays directly into an insulated crucible to ensure that heat can be sufficiently accumulated to reach target casting temperatures. To validate the insulative performance of the crucible design, the team fabricated a prototype crucible for thermal cycling tests in a box furnace, which closely controlled the external temperature while a thermocouple on the inside of the crucible logged the temperature of liquefying aluminum feedstock. The experimental data was compared to a transient thermal simulation with boundary conditions set by the controlled external temperature. The feedstock temperatures predicted by the model closely aligned with the experimental data, with an average magnitude percent error of less than 2.5%, validating the insulative properties of the crucible as well as the team's ability to accurately simulate its thermal performance. To assess the performance of the tungsten probe, the team completed a ray tracing study in ANSYS SPIOS. These simulations validated that even with tungsten's typical reflectance range of 50 to 65%, the probe geometry traps over 94% of provided solar energy by reflecting rays downward towards the probe tip for further absorption. The geometry also ensured that the majority of heat flow was concentrated at the bottom of the tungsten probe for more effective conduction to the liquefying feedstock. With boundary conditions set by the ray tracing study and a finite element model validated by experiment, the team studied the heating of ISRU-derived feedstocks within the true lunar use case, with results showing that ACRE will be able to melt and cast 1.3 liters of aluminum feedstock in approximately 25 minutes, making it a promising candidate for the fabrication of mixed aluminum regolith metal matrix composite roads across vast areas of lunar surface. Similarly, ACRE will be able to cast the same volume of iron feedstock in approximately 115 minutes to be used for applications requiring elevated temperatures and mechanical loading, especially lunar landing pads.
The materials team verified the creation of metal matrix composites by manufacturing them both via mixing and sandwiching the regolith and metal. Pictured here is a high temperature mixture of 10 weight percent regolith and aluminum. Notice that the average particle size from our sample is much lower than expected from the regolith particle size distribution. This is indicative of a thermite reaction which would allow unique tuning of material properties. The material team also discovered a novel ALBI alloy with reduced surface tension compared to pure aluminum. Pictured here is an image of a drop from a goniometer which was used to tune the contact angle of the alloy to match expected surface properties of aluminum in ultra-high vacuum. Using this alloy, bricks could be cast in air with surface properties that mimic those expected on the moon. The vacuum induction furnace will play a vital role in the future materials development and characterization. The in-situ casting of molten aluminum under vacuum will be used to validate its wicking properties as well as potential for manufacturing of metal matrix composite.
Optimized plow geometries are used to furrow ditches in the lunar surface, which shape the casted material, limiting settlement and lateral motion of casted materials during use. The shape of the rover's plow, including mold depth, mold width, draft angle, and anchoring shape, can be easily exchanged to optimize for the casting of a particular product. An insulated regolith bed was constructed to both validate plowing geometries and methods, and to validate brick geometry and materials. The XYZ gantry enables 3-dimensional adjustments to plowing, while the large regolith bed minimizes edge effects. For rapid prototyping, a quick connect plow system was developed. Plowing consisted of raking the bed flat, plowing, and then using LiDAR to scan the grooves created in the soil. An LS Dyna simulation compared directly with simulated plowing performed on Earth. The tuned model is then used to simulate plowing of the regolith in lunar gravity. Lastly, materials were casted into the plowed regolith to form a brick. This brick was cross-sectioned and polished to verify surface properties, wicking, and adherence to the plowed shape.
Testing has validated ACRE's critical systems for solar power collection, heating of feedstocks, creation of lunar regolith molds, and casting of molten metal feedstocks.
Autonomous casting rover, constructing the Artemis generation's lunar future 1 acre at a time.